So again, this is just a time difference when we shift the thing 90 degrees. So this, the absolute value of this number, LV squared over 2C cubed, is what's important. Okay. So that's the amount of time that we fall behind, that one beam falls behind the other when we rotate the Michelson Morley apparatus by 90 degrees. That's the first line. So then on the second line, we go back to, that means that the distance one falls behind the other. Distance equals rate times time is c times that time. Now again, you say, well, why wouldn't we use the real time, which we're assuming if one of them, if the ether is traveling some direction, it's going to be somewhere between c minus v and c plus v. And the answer is because we know that v is much, much less than c. Otherwise, this would have been measurable through other experiments. Because v is much, much less than c, excuse me, this means that the difference between using c plus v and c minus v, or c here, would be a difference in distance, again, in like the 5th decimal place. And so it wouldn't matter. Oh, wait a second. I just realized I glossed over something here. I didn't do anything wrong, but I certainly have changed my tune, because this is v over c, which is about 10 to the minus 4, 10 to the minus 5, which gives us the decimal places here and here. But we're talking about v over c squared, which goes out another double the number of decimal places. So the first approximation is going to be out in the 10th place. The second approximation, because v over c squared, right here we wrote v over c. But if it's v over c squared compared to 1, then the first approximation is going to be different from 1 somewhere out in the 8th to 10th decimal place. The second approximation, the second order term, is going to be different from 1 in the 16th to 20th decimal place, depending on whether it's 10 to the minus 4, 10 to the minus 5. So, it so doesn't matter. Okay. So coming back here, we're saying that the difference in distance is still going to be, excuse me, I keep coughing, is going to be so small that it doesn't matter whether we use v minus c, v plus c, or c. And what we end up getting is that the difference in distance between beam 1 and beam 2, when we rotate the apparatus, is going to be given by the equation written that'll shift this by some known amount. Shift the interference pattern by some known amount. Sorry, I'm sure that some of you noticed I made yet another little error here. When I had a 4 on top and a 2 on the bottom, I said that was a 2 on the bottom. That should be a 2 on the top. So coming back here, this should be a 2 on the top, 2lv squared over c squared. So delta d is 2, that was not a 2, 2lv squared over c squared, or 2lv over c squared. And in order to shift the interference pattern by a full dot, right? So to take one of the dots in the interference pattern and have it move all the way down to the next dot, this would have to equal to n times lambda, where lambda is the wavelength of the light that they used, where n is equal to 1. N equals 1 would shift the pattern by a full, what's called fringe. This is an important word, a full fringe. The fringe is, this is a fringe, this is a fringe. Those are the fringes, the dots. And so if we shift it by a full fringe, that means we're taking one of the bright spots, we're moving it all the way down to the next bright spot. Or if we shift it by half a fringe, we're shifting a light spot to where the dark spot is. Anyway, for n equals 1, we'd shift the pattern by a full fringe. And what they were able to determine, I can't remember exactly what it was, that they could measure accurately up to 1/100th of a fringe, 1/100th of a fringe. So that means instead of n being 1, n would be 1/100th, and therefore, so let's just say this was their accuracy. They figured they could accurately measure a shift of 1/100th of a fringe. Then they could measure 2lv over c squared equals lambda over 100. Let's assume that they're using red light. It's good enough assumption. They probably were using something with a slightly lower wavelength, but 700 nanometers, let's just assume that's a good approximation. So just doing out the math for that example, I believe you get that the minimum, that V would, if the shift was 100th of a fringe, that V, the speed of the ether would be about 18,000 meters per second. And maybe it was 1,000th of a fringe. If they could measure 1,000th of a fringe, then it would be 1,800 meters per second. But they were not able to measure any fringe shifts, so they weren't able to conclude anything other than it was close enough to zero that they couldn't measure it. Just one more mathematical note, and that is that the V over C quantity comes up all the time because we're often interested in a body's speed relative to that of the speed of light. Because we'd like to compare the two, and so we actually define a quantity beta. Beta is equal to V over C. So we get 1 plus beta to the n is approximately equal to 1 plus n beta. If beta is much, much less than 1 is the same as saying 1 plus V over C to the n. I put it squared there, but it doesn't matter. Beta is not V over C squared. Beta is V over C. So that means that 1 plus beta squared to the n is even more approximately 1 plus n beta squared if beta is much, much less than 1. Because if beta is much, much less than 1, then beta squared is even much, much smaller than that. Okay.